Hi all, today we are going to discuss about the symmetrical components and how to calculate the symmetrical components. So for that, let us take for example, I am taking a load. So let us assume the load is having a simple resistive load and this is my phase A, this is phase B and this is phase C, and let us assume the load is balanced. That means all the phases, the amount of the load is same. So when the load is same, obviously the current passing through that will be same. So this will be value of IA. So this is the value of IB and this is the value of IC. So in this case, the value of this IA will be equal to value of IB will be equal to value of IC, but they are displaced by 120 degrees. So the sum of the vector IA plus IB plus IC is equal to 0. Why? They are displaced by 120 degrees. Instantaneous values becomes equal to 0, but their magnitudes are same. So if you want to analyze this circuit, we can analyze on the per phase basis, like we have discussed in the last class, the single line diagram or the impedance diagram, per unit impedance diagram, we can draw for a case of single phase. We can analyze for the single phase, and for three phase power if you want to calculate, you can simply multiply with 3. That is the advantage of going for the balanced load. So same thing is the case for symmetrical fault. That means if the fault happens symmetrical, that means all the three phases are short circuited. So in that case, the short circuit current through all the phases will be same. So even in this case also, we can take one phase and analyze using that. So let us take the case if the load is unbalanced. That means the different phases are having the different values of the resistors. So let us take for example, this resistance is R1, this resistance is R2, this resistance is R3. So in that case, the value of IA, this is the value of IB and this is the value of IC. So in that case, this IA, magnitude of IA will not be equal to magnitude of IB will not be equal to magnitude of IC. So as the currents are not same, so we cannot go for the single phase analysis. So we have to go for the three phase analysis only. So analyze using the three phase network. So how to analyze using the three phase network? We have already discussed in basic electrical engineering. So effect of unbalanced loading in a star connection. So you can please refer there. I have solved the numericals there. So if you see the practically what are the different type of faults that happens in practice, the three phase faults accounts for about 5%. And line to ground fault happens for 10% of the cases, and line to line faults happens for 15% of the cases, whereas the line to ground fault happens for nearly 70% of the cases. Or we can tell that out of the total faults that happens in our power system, only 5% faults are three phase faults or the balanced faults, whereas the remaining 95% of the faults are unbalanced fault. So for the case of unbalanced fault, the magnitude of the currents will not be same. That means IA will not be equal to IB will not be equal to IC. So it will not be same. So that's why we cannot go for the analysis based on the single phase circuit. Only for balanced fault or three phase fault, magnitudes are same. We can go for single phase analysis, but for unbalanced loading, we cannot go for single phase analysis. We have to go for three phase basis. So the alternate way and most easiest way of analyzing these type of circuits is to convert these whatever the currents are there or the voltages are there, this unbalanced components can be converted into the symmetrical components, where the three voltages and the currents are transformed into three sets of balanced voltages and currents, which are called as the symmetrical components. So by using the symmetrical components, the analysis becomes easy. What are those symmetrical components? Let us take for example, I am taking a voltage VA. The voltage VA will be the combination, this is the voltage of phase A, will be the combination of three sequence component. One is the positive sequence component, second one is the negative sequence component, and third one will be the zero sequence component. Similar is the case for the phase B and similar is the case for phase C. And these symmetrical components are like that. So this is the first component. This component, this VA1, VB1 and VC1, this is called as the positive sequence. The meaning of the positive sequence is the MMF produced by this. If you are giving this positive sequence component to your alternator, so the MMF produced by the positive sequence component will rotate in the same direction as the rotation of your rotor. So that is called as the positive sequence component. That means under ideal conditions, whatever EMF is produced by your alternator, that is called as the positive sequence component. So in the positive sequence component, if I am taking VA1 as my reference, that means A phase, positive sequence 1. So the phase B voltage will lag behind this by 120 degrees and phase C will lag behind VC by 120 degrees. Or if you are taking in the clockwise direction, the sequence that will be followed will be ABC. So the sequence that is followed is ABC. So that's why it is called as positive sequence. Now coming to the negative sequence, again if I am taking the A phase as my reference, here it will rotate in the opposite direction. So here also the voltages are displaced by 120 degrees, but they will rotate in the opposite direction. So what is the meaning of this? If the negative sequence component is given to the alternator, then the MMF produced by this negative sequence voltage will rotate in opposite direction to the rotation of the rotor. So that will create huge value of the heating. So this we have already discussed in the synchronous machines. So here you can see if this is my VA2, the VB2 is leading VA2 by 120 degrees and VC2 is leading it by 120 degrees. It is rotating in opposite direction. That ABC sequence is rotating in opposite direction. So you can see here, this is my ABC, it is rotating like this, but here the ABC sequence is rotating in clockwise direction. First A is coming, then B is coming, then C is coming. So here the sequence is ABC, but here if you take in the clockwise direction, the sequence is ACB. That's why it is called as negative sequence. Again, in the negative sequence also, the component, that means the magnitude of VA2, VB2 and VC2 will be same only. Similar is the case, the magnitude of VA1 will be equal to VB1 is equal to VC1, but they are displaced by 120 degrees. But the magnitude of VA1 may not be equal to VA2. So similar is the case, the zero sequence, the name the zero sequence indicates that those phasors are displaced by 0 degrees. That means these phasors are displaced by 0 degrees from each other. Again same thing, the magnitude of VA0, VB0 and VC0 will be same, but their magnitude may or may not be equal to VA1 or VA2. You have to remember this. So now if you want to calculate VA, so what I have to do? I have to do the sum of VA1 plus VA2 plus VA0, the phasor sum of those things. That means how to do this one? If I want to calculate VA, so I am doing for one phase, this will be equal to VA1 plus the second one is VA2. So VA2 is like this. So VA2 I am adding to this one. So this is my value of VA2, and for VA2 I have to add VA0. So I am adding VA0. So when you are adding these things, so that gives your resultant value of voltage A. So this gives my value of VA. So similar is the case, the other phases also we can calculate in this way. So different voltages will be in the different magnitude as well as the phase. They may not be displaced by 120 degrees under unbalanced conditions. So details of these things we will discuss in the coming lectures. So here my major concern is to discuss about the sequence components and their derivations. So that's why I am proceeding further. So by taking the phase of phase A as my reference value, the symmetrical components of phase B and C can be derived in terms of components of phase A using an operator, complex number operator alpha. So this complex number operator alpha, it is having a magnitude of unity and its rotation is having a phase of 120 degrees, that is plus 120 degrees. So what does it mean? That means when any vector is multiplied by this vector operator alpha, then the vector magnitude remains same, but the vector will rotate in anti-clockwise direction by 120 degrees. It will rotate in anti-clockwise direction by 120 degrees. So this vector operator I can represent like this. The value of alpha is equal to 1 at an angle of 120 degrees. That means it will displace by 120 degrees in anti-clockwise direction. Or this I can represent as cos theta plus j sin theta, magnitude is equal to 1. This is equal to cos 120 plus j sin 120. Or this I can represent in form e to the power of j 120. Because e to the power of j theta is equal to cos theta plus j sin theta. So same thing I can represent in this form. So let us see what is the property of this alpha so that we can proceed further. So what I am doing, I am taking alpha square. Alpha square means alpha multiplied by alpha. So alpha is nothing but 1 at an angle of 120. I am multiplying again with 1 at an angle of 120. So we know that whenever you are doing the product of two polar coordinates, the magnitudes will multiply with each other and angles will add to each other. So when you are doing multiplication, so if you have doubt about how to do this phasor algebra, this thing you can refer to my basic electrical engineering playlist. So there I have discussed how to do the phasor algebra. That means product, sum and other things in rectangular and polar coordinate systems. So I hope you already have the basic idea. So I am proceeding further. So this alpha square will be 1 at an angle of 240 degrees, or I can write as e to the power of j 240, or this will be, so it is nothing but, so if I am taking my reference value, so this is my reference value. So alpha, what it will do? Alpha will shift it by 120 degrees. So this is my value of alpha. So it will be leading by 120 degrees. So it is having a magnitude of 1, leading by 120 degrees. If I am taking alpha square means I am adding alpha, again shifting further by one more alpha. So this value will be alpha square. So what alpha square will do? It is having a magnitude of 1 only, but shifting by 240 degrees. So now this alpha square, how much it is rotated? It is rotated in counterclockwise by 240 degrees. That's why it is called as plus 240, or same thing I can represent in the opposite direction. So this is in minus 120. That means with respect to my reference, this alpha square is lagging behind this reference by 120 degrees. That's why I can write it as e to the power of minus j 120. E to the power of minus j 120. So you can see here, compare with alpha. Alpha is equal to e to the power of j 120. Now it becomes e to the power of minus j 120, because this is nothing but conjugate of this one. Because what is the meaning of conjugate? Conjugate means the imaginary part, whatever is there, you have to change the sign. So this is nothing but the sign of the imaginary component is changed. The real component is not changed, imaginary component sign is changed. So it becomes minus. So that's why we can write this as the conjugate of alpha. Getting this one? Or using this relationship, I can tell that this alpha square conjugate, if I take, that means conjugate of e to the power of minus j 120 will be e to the power of j 120. So that will become equal to alpha. So now coming to alpha cube, that means you have to shift 3 times. So when you shift 3 times, you can see here 120, 240, one more shifting you do. So you will reach the reference point again, because that means this alpha to the power of 3 will be coming here. So when you are taking alpha to the power of 3, I am completing one rotation, or I am completing an angle of 360 degrees. Because 360 degrees means one cycle is over. So 360 degrees, when one cycle is over, we can take it as 0 degrees also. So e to the power of 0 will be equal to 1. So that's why this will become equal to 1 only. So that's why alpha cube will be equal to 1. So from these relationships, I can write that 1 plus alpha square. So 1 plus alpha square, if you take it, so these are of 3 vectors. Each vector, one vector is having angle 0, second vector is having angle of minus 120 degrees, and third one minus 240 degrees. Or these are the vectors, that means I am taking the sum of 3 vectors. All are having a magnitude of 1, but displaced by 120 degrees. What is the instantaneous value of these things? So this will be equal to 0. So you can just apply it and check. Take the magnitude is equal to 1 and take the angle is first one as 0, second one 120 and third one as 240. Take the sum, you will get the magnitude is equal to 1. So from this, we will make the conclusion that if any numerical it is given, I want to calculate alpha to the power of 7. So what will be the alpha to the power of 7? This will be equal to alpha to the power of, every 3 it is completing one cycle. So this I can write in the form 3 into 2 is 6. So this is 6 plus 1. So alpha to the power of 6 will cancel out. So only alpha will be remaining. Same thing is the case if I tell that alpha to the power of 27, this is nothing but 7 times 3, or this is nothing but alpha to the power of 0 or its magnitude. It is equal to alpha cube or alpha to the power of 0, which is equal to 1. Similar is the case if I take alpha to the power of 5. So alpha to the power of 5 means this I can write as alpha to the power of 3 plus 2. So 3 will cancel out, so alpha square will remain. So let us see how to represent the component in terms of my basic components. So I am representing the positive, negative and 0 sequence components here. So this I can write as VA1. This is my value of VB1 and this is my value of VC1. Similarly for the negative sequence component, so this is my value of VA2 and this will be my value of VC2 because it is an opposite sequence. This will be my value of VB2. Similarly 0 sequence component, so these are my 0 sequence component. This is VA0, this is VB0, this is VC0. So now we will try to calculate this one. So I am taking VA1, VA2 and VA0 as my reference and calculate the remaining component using the vector operator, this operator alpha. So if you want to go to VC1, how can I get this? Multiply VA1 with alpha. That means it is proceeding by 120 degrees. That means this is plus 120 degrees difference is there. So this I can write as VA1, I can just multiply with alpha. So alpha times of VA1 will give this. So if I want VB1, this will be nothing but I am shifting by 120 plus 120, 240. So this will become alpha square times of VA1. Getting this one? So similar is the case here, VC2 will become equal to alpha square times of VA2 and VB2 will be equal to alpha times of VA2. So now coming to VB0, VB0 will be equal to VA0 and VC0 is equal to VA0. That means if you can calculate the value of VA1, VA2 and VA0 from the unbalanced loading values, that means whatever is your load values and the load condition, either currents or the voltages, we can calculate the remaining components using this vector operator. That means alpha, alpha square and these things. So I am making the summary of these things here. So the summary I can write in this form. So this value of VA, VB and VC. So this I can write as 111 alpha square alpha 1 and this will be alpha alpha square 1 of VA1, VA2 and VA0. Agree with me? So in this form I can write the value of VA. So for example, VA is equal to VA1 plus, because 1 multiplied by this, VA1 plus VA2 plus VA0. Similarly, if I want to calculate my value of VB, VB is nothing but, so VB is nothing but VB1 plus VB2 plus VB0. So what is VB1? Alpha square times of VA1 and VB2 is alpha times of VA2 and VB0 is 1 times, that means VA0 only. So same thing I have written here, alpha square alpha 1. So similar is the case for VC. So VC, you can create VC1 is alpha times is coming here and here it is coming alpha square and here it is 1 times. So alpha, alpha square 1. So alpha, alpha square 1. So I think this is clear up to now. So this I can write in this form. So the value of a VP will be equal to A times of Vs. So let us take it as equation number 2. So where the value is the operator of the original phases. So this is nothing but original phasors, or this is the phasor of the respective phases. So A is a vector or the matrix operator and this value is, this Vs is the vector of symmetrical components. So I have just tried to correlate this one. So this one is this one and this table will be this one and the value of this one is this one. Getting this one? So now this table operator I am just taking it outside. So this I am writing as A is equal to 111 alpha square alpha 1. So alpha alpha square 1. This is the table we get. So let us take it as equation number 3. So from equation number 2, because I want to calculate my these symmetrical components. So symmetrical components I can get from this one. So the value of the symmetrical component vector Vs will be equal to A inverse, because you can see here Vp is A times of Vs, or Vs is equal to A taken this side, it becomes A inverse, because matrix 1 by A becomes inverse of this matrix. So A inverse multiplied by Vp. Agree with me? So this I can write as A inverse multiplied by Vp. A inverse multiplied by Vp. So this I am taking as equation number 4. So if you calculate the value of A inverse using this one A, so use this A inverse will be equal to 1 by 3 times of 1 alpha alpha square. You can please check it, you will get this one. I am directly writing this to save some time. So alpha square alpha. So this will become 1 1 1. So this is the value. So this I am taking as equation number 5. So from here I can conclude that I can write my value VA1, VA2 and VA0, because this Vs is nothing but this one. So VA1, VA2, VA0, so this will be equal to 1 by 3 times of 1 alpha alpha square, 1 alpha square alpha, 1 1 1 times of, so same thing, this Vs I have represented here, this is my value of A, and I have to multiply with Vp. So Vp is the main vector, the main vector is Va, Vb and Vc. So using this I can calculate my sequence components using this matrix. So from this I can write my sequence components are nothing but Va1 will be equal to 1 by 3 times of Va plus alpha times of Vb plus alpha square times of Vc. Similarly, the value of Va2 will be equal to 1 by 3 times of Va plus alpha square times of Vb plus alpha times of Vc. Similar is the case, I can write Va0 is equal to 1 by 3 times of Va plus Vb plus Vc. So this I am taking as equation number 6. Getting this one? So similar way I can write for the currents. So I can write that similarly the current I can write as Ip is equal to A times of Is. So from this I can write my value of As is equal to A inverse times of Ip. You agree with me? So that means symmetrical components of current I can write in terms of the normal components. So I am directly writing the matrix for the same because same derivation will be there. So this is Ia1, Ia2 and Ia0. So this will be equal to 1 by 3 times of 1 plus, so this will be 1 alpha alpha square and 1 alpha square alpha 1 1 1 times of Ia, Ib and Ic. This way we will get it. So to understand this concept completely, so I am taking one example. The line to ground voltage on the high voltage side of a step-up transformer are 100 kV, 35 kV and 40 kV on phases A, B and C respectively. So I am trying to note down the data simultaneously whenever I am reading. So VA is given as 100 and VB is given as 35 and the value of VC is given as 40 kV. They are in kilovolts. And on phases A, B and C respectively, the voltage of phase A leads B by 90 degrees. Let us take A as my reference. So it is telling that phase A is leading B by 90 degrees. What is the meaning of this? B is lagging behind the phase A by 90 degrees. Lagging means minus 90 degrees. So with respect to A, and lags that of phase C by 180 degrees. That means A is lagging C by 180 degrees, or with respect to A, C is leading by 180 degrees. This is nothing but leading. So that's why I can write it as 40 at an angle of 180 degrees. So these are in kV. So now it is asked to calculate the sequence component. So sequence component, we know the formula. So we know the value of VA1 will be equal to 1 by 3 times of VA plus alpha times of VB plus alpha square times of VC. So let us see how to calculate this one. So this will be 1 by 3 times of VA is 100 at an angle of 0 degrees plus alpha means 120 and VB is 35 at an angle of minus 90 degrees. This will be multiplied by 1 at an angle of 120 degrees. So 1 is there, I am neglecting, so 120 degrees plus VC is 40 at an angle of 180 degrees. So this will be multiplied by 240 degrees because alpha square is nothing but 240 degrees, or you can write it as minus 180 degrees also, whatever you feel convenient. So I am writing minus 120. Even you can take plus 240, you will get the same answer. So this will be nothing but 1 by 3 times of 100 at an angle of 0 degrees plus 35 at an angle of, so we know that whenever you are doing the product of 2 in polar form, the magnitudes will multiply and the angles will add to each other. So you have to add these things. This is minus 90 plus 120. So this becomes equal to 30 degrees. And the third one will be 40 at an angle of 180 minus 120. So this becomes 60 degrees. So we know that the addition and subtraction are easy by converting them to the rectangular form instead of doing in polar form. So if you want to know about why we have to convert and these things, I have derived in phasor algebra in basic electrical engineering playlist. You can please refer to the lecture on phasor algebra. So there I have explained and proved why it is like this, why we should do like this, and how to calculate. You please refer there. So this I am directly converting to rectangular form. Polar to rectangular, how to do? Polar to rectangular will be magnitude cos of the angle plus j times of magnitude and sine of the angle. Magnitude multiplied by sine of the angle. So when you do this, so this will become 100 plus j0. Similarly, second one if you do, this will become 30.31 plus j 17.5, and third one will become 20 plus j 34.641. So this will become 1 by 3 times of all the real components we have to add up. This will become 150.31 plus j 52.141. All imaginary components are added. So this will become equal to 50.1 plus j 17.38. So we got the value of VA. So similar way I can calculate the value of VA2. So VA2 will be equal to 1 by 3 times of VA plus alpha square times of VB plus alpha times of VC. So this will be equal to 1 by 3 times of 100 at an angle of 0 degrees plus this is 35 at an angle of, so I have to multiply with alpha square. Alpha square means minus 120. So whatever is the angle of VB I am adding, so I am directly writing this answer. So this will become 150 plus third one, when you multiply with alpha, it becomes 400 at an angle of 300. You can just try to do it. So this will become equal to 1 by 3 times of, this I am converting to rectangular form. This will become 100 plus j0 plus minus 30.31 plus j 17.5, and third one will be 20 minus j 34.64. So this is the value we get it. So this is the value. So this one will be equal to 1 by 3 times of 89.69 minus j 17.14. So if you calculate this one, so this will become equal to 29.9 minus j 5.71. This is the value. So similar is the case, the third one I can calculate. VA naught will be equal to 1 by 3 times of VA plus VB plus VC. So 1 by 3 times of, so that VA will be, I am writing in the rectangular form, so 100 plus j0, and second one will be 0 minus j35, and third one will be minus 40 plus j0. I have just converted to rectangular form. So now if I do the sum, so this will become equal to 20 minus j 11.67. So this is the value I got. So all these values are in kV, kilovolts only. So this way I have to calculate my sequence components. So once the sequence components are obtained, then how to do the analysis and other things I am going to discuss in the coming lectures. So here today we have discussed about the voltage and the current, how to calculate the sequence component. So next class we are going to see how to calculate the power using this sequence component. How much simple it will be by using the sequence components to calculate the power. So that we will see in next class. So after that we will go for the different type of fault analysis, and there we will prove that using this sequence component the solution of numerical is so much easy compared to analyzing with the three-phase circuits. So that means analysis using three-phase systems. So I hope the basics are completely clear to you. If you still have any queries, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you very much.